Okay. Got that going. All right, so last time, I think it was last time that we introduced NFAs. Maybe it was the time before. But thus far, we've been talking about DFAs and NFAs. What's a DFA? A deterministic finite automata. An NFA is a non-deterministic finite automata. So they're both finite state machines. The big difference between a DFA and an NFA was that with a DFA, you had to give an arrow showing where you were going on every input symbol. So every arrow had to be on there, and you couldn't have two arrows with the same inputs coming from the same state. So I couldn't have something like this. I couldn't have on A go to here and on A go to here. That would not be deterministic. With a non-deterministic finite automata, you don't have to write all your arrows. And if there's no arrow for an input symbol, it's just understood you died. We instantly reject, right? And stuff like this was allowed. You can make a choice about what to do when you saw an A, and that was perfectly acceptable. And what we proved, the astonishing thing, is that NFAs are no more powerful than DFAs. In fact, they're logically equivalent. So if we're trying to show that some language is regular, we can construct a DFA to recognize it, and that proves it's regular. Or we can construct an NFA to recognize it, and that proves it's regular. So ultimately, what we're interested in is showing languages are regular. And so now we can use either an NFA or a DFA to show that the language is regular. NFAs and DFAs are logically equivalent. Does everything I say just so far make sense? So now we're going to go back to showing that our three regular operations, union, concatenation, and star, we're going to show that our three regular operations are closed on regular languages. What do we mean by that? So remind us about closed operations on numbers for a second. Addition is a closed operation on the integers, or on the natural numbers. If I take two natural numbers and I add them together, it's still a natural number. Subtraction is not a closed operation on the natural numbers. If I take two natural numbers and I subtract them, it might be a natural number, but it might not be a natural number. 9 minus 2 is not a natural number, it's -7. Sorry, other way, 2 minus 9. Thank you, appreciate the expression on good feedback. That sets up the wrong. So, when we're saying that we're going to show that these operations are regular, what that means is if I have a regular language and I union it with a regular language, we're going to prove that's regular. If I have a regular language and I concatenate it with a regular language, we're going to prove that's regular. Or if I have a regular language and I star it, we're going to prove that's regular. That's a big picture of what we're interested in here for the next little bit. And so we're going to do each of those three proofs I just told you. We already did the union proof before with a DFAs. Now we're going to do it again with NFAs because it becomes stupid simple. All three of these proofs are really simple with NFAs. The words might look like a bit much, but when I show you the basic picture for it, you'll instantly get it. Here's the basic picture for it, and then we'll walk through each of the basic proofs. So starting with the union. Union we think about like OR. If I want all the strings that end in a 0, union with all the strings that end in a 1, that's all the strings that end in a 0 or a 1. Right? So if N1 here is some NFA, recognizes who cares. Here's its start state, it recognizes some language, and there's its accept state. Just some general machine, recognizes some strings. And then here's some other machine, which recognizes some other set of strings. And I want to now build a machine that recognizes the union of these two languages, recognizes all the machines that this accepts or that this accepts. All we have to do is add a new start state. Add a new start state, so now this is my start state. And I make my start state go to this one's start state and this one's start state. I keep slipping down. On an epsilon transition. So we make that's no longer start, we make so that's no longer start, and we just add this new start state. So now, if this machine would have accepted a string before, we can empty over and then start reading the input and we'll accept. And if this string would have accepted an input before, we can just empty over, start reading the string, and it will accept. And remember, NFAs accept if it's possible, if there's any possible path for the string to accept. And so the string can always take either one of these paths without using one of its input symbols. That makes sense? So this is, in general, how we create a machine that recognizes a union. Make sense? Now, we'll write that out with our proof. So now the proof. If A1 and A2 are regular, meaning A1 and A2 are regular languages, then so is A1 union A2. If you have two regular languages and union them together, it's still a regular language. That's what we're proving. Okay, so let's prove it. Let A1 and A2 be regular languages, and let N1, here's its definition, and N2, here's its definition, be the NFAs recognizing them respectively. So N1 recognizes A1, N2 recognizes A2, and notice the only way they differ basically is in their subscripts. The states of N1 are Q1, its transition function is delta 1, its start state is Q1, its accept states are F1. And we assume that they both have the same language. It doesn't really change the proof if you assume, or the same alphabet. It doesn't really change the proof if you assume they have different alphabets. You just union the alphabets together. That's why we never change sigmas in any of these proofs, because it's trivial. But anyway, so here's a machine that recognizes A1. Here's a machine that recognizes A2. How do I know that there is a machine that recognizes A1?
Because by definition, that's a regular language.
Yeah, we said let A1 and A2 be regular languages. What does it mean to be a regular language? By definition, a regular language is a language that is recognized by a DFA. And then we proved last time that you can also say a regular language is a language that's recognized by an NFA. So I have two regular languages. There has to be some two NFAs in existence. Some NFAs, I know nothing about them, but there has to be two NFAs that recognize those languages. Otherwise, they won't be regular. So we haven't cheated so far. We're just using information we know, and we're labeling parts of those NFAs.
Are there some languages that an NFA can recognize that a DFA can't? I think we went over this last
No.
class. Okay, sorry.
They're logically equivalent.
Okay, that makes more sense.
Okay. So here's our two machines that recognize these two languages respectively. Basically, same as I have our picture down here. Okay, so now we're going to define some new things. I'm going to define a new queue. This is going to be the set of states on the new machine I'm describing. Because how am I going to show that A1 union A2 is regular? The only way we know right now on how to show that a language is regular is to show that we can find some NFA or some DFA that recognizes it. So my proof, the whole job of my proof is to construct some NFA that recognizes this language. And the NFA I'm going to construct is this big one right here. That's ultimately what I'm doing in words, is I'm reconstructing this thing. So what are the states of this whole thing now? It's all the states of this machine, and all the states of this machine, along with the state of this one right here, which we're going to call Q0. So the states of my new machine, Q, are the states of my first machine, Q1, union with the states of my second machine, Q2, union with the set containing Q0. Make sense so far? Okay, what are my accept states to my new machine?
The accept states of both machines.
Yeah, the accept states of this machine union with the accept states of this machine. So F is going to be F1 union F2. And now our transition function, it looks like a mouthful, but it's really not that bad. We just have four possible cases that we need to take care of with our transition function. So our transition function, first off, if we're transitioning to a state up here, what should we do? Just whatever this machine was already doing. That's what this is saying. So our transition function, if we're in some state Q, and our input symbol some state A, if Q happens to be in Q1, so if Q is one of these states, then just do whatever delta sub 1 was doing with that exact same input. So if Q happens to be in this machine, then our transition function is just going to do whatever the transition function for this machine or this machine was already doing. That's delta sub 1. So our new machine, delta, on input QA, does whatever, sorry, I think I said that wrong. Our new transition function, delta, on input QA, does whatever this thing's transition function was doing with those same inputs if our state was in the first machine. Similarly, it does whatever our second transition function was already doing if our state is in the second machine. If we ignore this part of the picture over here, if we're over either in this circle or we're down in this circle, we can just keep transitioning how we already were, in other words. And it's only these transitions right here that we need to make explicit and add to this. So these two say, if you're in here, this one says, if you're up here, just keep doing what you were doing. If you're down here, just keep doing what you were doing. Now, if you're in Q1 or Q2, oh, sorry, our transition function goes to Q1 or Q2. So our transition function goes to Q1 or Q2 if our state that we're talking about is our initial state and our input symbol that we're talking about is epsilon. So this one is describing these two arrows. So if our input state is Q0, which is our new start state, and our input symbol is epsilon, then we go to Q1 or Q2. You following that? This is the output. Here we were always listing the output for a particular input. What's the input on QA? If that Q was in here, it's the same as the output from this transition function. When I plug it into this transition function, it spits out an output. It would have been a set of states. When you give the transition function input, it spits out a set of states, right? So go to the set of states this was already going to, or go to the set of states this was already going to. Here we explicitly say, if you're at this state and your input symbol is an epsilon, we're going to go to one of these two states. You have your choice. And then finally, if you're at Q0 and your input symbol is not epsilon, then we go nowhere. We crash. We don't accept those. You don't get to read anything except epsilon at our new start state. So it seems like a mouthful, but it's really just describing exactly what we did with this picture.
Can you read anything other than epsilon?
Not from the start state.
So do we need that last piece then?
Do we need this?
Yeah. If you can't read anything about epsilon from the start anyways.
Well, what should you do if you read? We need to tell the machine what to do on that input, because it's still in the domain. So the domain still includes something like Q0, comma, assume our language here was zeros and ones. So Q0, comma, 0. That's still in the domain, so we still got to map it to something. What are we going to map it to? The empty set, because we don't do anything on that input.
Oh, okay, I see.
So remember, with our table, if we were to build our table, we still need to explicitly say what to do on every combination of input. Make sense? Okay, so that was recognizing the union of two languages. Next one is going to be recognizing the concatenation of two languages. That's where the first part of your string comes from this language, and the second part of your string comes from this language. Remember doing some concatenation? We did some examples of these operations already. Okay, so how would we do that? Come back to our picture. So say once again, I've got these two NFAs here. This one recognizes all the strings for A1. This one recognizes all the strings for A2. I want to build a machine now that recognizes the concatenation of the two strings. A1, then A2. What am I going to do? I'm going to go from all the accept states here. I'm going to go over to the start state of this thing. So that ties in with it well. On an epsilon transition. I'm no longer going to call these accept states, so you can no longer accept here, because that's only the first part of the string. And we'll still leave those accept states. So if you get through this machine, that means you had some input that this machine could accept. And then you come here, and then if you get through this machine, that means the string you had remaining was some input that this machine could accept.
So your string will transition over the moment it reaches an accept state.
Not the moment. We can choose when we want to transition over.
Oh.
We now have choice. That's why we couldn't do this with a DFA, because we didn't know when to transition over. We didn't know what choice of where I should split my string would make the second half of my string work. The powerful thing about NFAs is trying every single possible choice in parallel. And if there is any choice that makes this work, then it accepts.
So there is a DFA that does the exact same thing.
There is a DFA that does the same thing. It's just a lot harder to reason about. Where with an NFA, that was trivial reasoning. Make sense?
So you could possibly end up getting multiple strings then, right?
You can only, this new machine can only accept if this first half could have accepted
Right.
and the second half could have accepted. Which means there is some way to split it, such that the first half came from this language and the second half came from this language.
And there could be multiple ways to split it.
There could be multiple. But if there's some way to split it, then it's in the union of the, or it's in the concatenation of the languages.
Okay.
And the trick was figuring out where to split it. With non-determinism, we don't care where to split it. As long as there is some way to split it, the machine will figure it out. Right? And you remember, when we converted an NFA to DFA, what did we essentially do? We had a state keeping track of every possible combination of states in tandem. And that's the way you convert it. So it's like you do everything in parallel, just with a big DFA. Because there's only a finite number of states you need to keep track of, so it blows up exponentially, but hey, it's still finite. So we're fine. Anyways, so now let's say this exact picture, but now with our proof. Same picture. So if A1 and A2 are regular languages, so is A1 concatenated with A2. That's what we're proving. So let A1 and A2 be regular languages, and let N1 be described the exact same way we did over there. Q1, sigma, delta 1, Q1, F1. And N2 be the exact same way we described over there again. And they're the NFAs recognizing N1 recognizes A1, N2 recognizes A2. Okay. So what are our new states for our new machine, big N, going to be? Just the union of these two sets of states, right? We didn't add any states. We didn't add any states, so our new set of states is just our first set of states union with our second set of states. Now, our transition function, sorry, forgot that thing. Transition function on this one, bit more complicated, but I think you'll understand it. What do we do if the state we're reading is in our first machine, but it's not one of the accept states? So if we're at a state like right here, reading some input, which isn't one of the accept states, what should we do with our transition?
Keep following whatever.
Just go wherever it was already going. So if your input, if Q is in the first machine, but it's not one of its accept states, then just keep doing whatever delta sub 1 was doing. So this transition function does whatever the first machine's transition function was doing. If Q was in the first machine states, and Q was not one of the first machine's accept states. Okay? Now, what about if Q was an accept state, but the symbol it's reading is not the empty symbol? So again, I'm right here. My input is not the empty symbol, and I get some symbol. What should I do?
There's two options, right?
No, if I'm in this state, and I'm not reading the empty symbol, what should I do?
You start the next. You just you go down to the next one, right?
No, I don't go down to the next one. I only do that on an epsilon.
Oh, you keep going.
I just keep doing whatever this machine was already doing.
Right.
I only transition down on an epsilon. So, if we're in the first machine's accept states, and we're not reading the epsilon, we're not taking the epsilon transition, just keep doing whatever the first machine was doing. Now, let's say that we're here and we're reading an epsilon. Now what do?
Go on to the next machine.
We go on to the next machine, or maybe this machine up here also had some epsilon transitions. So we go to the next machine, or we do whatever this machine was doing on epsilon transition. We have both options available to us. Remember, we can make choices with these NFAs. So we have both those choices available to us. So if we're in the first machine's accept state, and we're reading the empty string, do whatever the first machine was already doing in that case, union together with the possibility of going to the next machine's start state. So you can do whatever this machine was already doing when it ran an epsilon, or you can go down here and start this machine. And then finally, if we're down here and we read some symbol, what do? Just whatever this machine was already doing. So finally, we do whatever the second machine was doing if our state is in the second machine. If we're already down here, you just do whatever this machine's doing. That make sense? All right? So then that new machine that we just constructed is going to be the NFA that recognizes the concatenation of those two languages. Therefore, the concatenation of those two languages is regular, because we found some NFA that recognized it.
Remind me what's the opposite of regular language? What is it? What does regular language mean? Like
Regular language means a DFA can recognize it.
Oh, right, okay.
That's its definition. Intuitively, regular languages are like the easiest languages to talk about. We're going to have this little bullseye of, and another way to think about it is, it's like they're the easy problems to solve. You're not used to this way of thinking about it yet. You will become the end of the class. That recognizing a language and solving a problem are logically equivalent. And so recognizing a regular language is kind of like solving easy problems. And then we'll recognize languages generated by context-free grammars, which are a bit harder. Then we'll look at all the languages that can be recognized by a Turing machine in general, which is all the problems that computers can solve. And then we'll look at problems that are out here, which we call undecidable. And they're problems that computers in general can't solve. So that's a hierarchy. And so right now we're completely interested in just this middle part.
And to get this right, this was the concatenation, the one where the accept states.
This one's the concatenation.
Okay, and the other
We
one was
hooked
the
this onto the front of this thing.
The other one was the union, where.
The other one was a union where we were kind of like doing both of them in parallel.
Yep. Okay. Got it.
Okay. So that's that. Now, next one. Next one is the star of a machine. And that one's picture is different enough that it's easier to just redraw it out. So I've got some machine here. Here's its start state. Does whatever it does, dot, dot, dot. Eventually we get to some accept states, however many, right? This will recognize some string. Say, for example, that it recognizes a string 1, 0, 0, 1, 0 is one of the strings that it recognizes. And if you read that input, you eventually get to an accept. Now we need the one that would recognize the star of this string as well, which means we can do this string as many times as we want. So not only should it recognize 1, 0, 0, 1, 0, it should also recognize 1, 0, 0, 1, 0, 1, 0, 0, 1, 0. And we can do that as many times as we want, including no time, so it also has to recognize the empty string. So I'll put a circle around the machine that we started with, and that way you can see what we add. Or maybe I'll just call this Q1, so that we remember that was the start state to begin with. So, I guess we can. So now how do we construct a new NFA which recognizes the star of it? We're going to create some new start state, stick it out here. We'll call that Q0. Q0 will go to Q1 on the empty string. Q0 will also be an accept state, so notice now we accept the empty string. And we will create arrows from accept states here to our start state here on the empty string. So you can read some input string, and then you can restart and go again as many times as you want.
Isn't the empty string going to Q1 just making so it doesn't accept it?
Yeah, it doesn't
If you
accept
read it and
Q1.
it goes to Q1.
Think about these epsilons as I can go from here to here without reading an input if I want. We can also just accept. If we just accept, what was the string we read?
Empty, yeah.
It was an empty string.
what he's saying is the only reason we don't go straight to Q1 is just so that we can accept the start.
Right, Q1 might have been doing something. Q1 might have had something like 0 here, going back to itself.
Yeah.
And so just making that accept state, we might accidentally be accepting strings that we didn't want to before. So making this an accept state is just to explicitly make sure that we can get the empty string, and then putting arrows from our previous accept states back to our new start state makes that we can loop the machine and restart as many times as we want. Make sense? So notice we added one new state, and we added 3 epsilon transitions. And that's what we're going to say over here. So if A is a regular language, so is A star, let N1 equal to Q1 sigma delta 1, Q1, that's its start state, and F sub 1 be the NFA recognizing the regular language A. Now we'll construct our new transition function, delta, and what's it going to do? Well, first off, if we were in our existing machine, and we're not in one of its accept states, what do?
We keep doing
Just keep doing whatever it was already doing. So, if we're in the initial states that we started with in our machine, and we're not in one of its accept states, we're just going to do whatever the transition function delta 1 was already doing. Right? Now, if we're in one of its accept states, but we're not reading epsilon, we're not reading the empty string, what do? Just keep doing whatever that machine was doing. So in the case where we're in the accept states, but our input is not the empty string, just do whatever the machine was already doing. Okay, what if we're in an accept state and we do read epsilon? We can keep doing what this was doing, because maybe this machine happened to have an epsilon transition to this state. So we do whatever this machine was doing along with going back to the start. The machine has a choice. So in that case, you can do whatever the machine was already doing, or you can go back to the start state. If your state was in one of the initial accept states and we're reading the epsilon transition. Right? Now, let's see. Now, if you're Q naught and we read epsilon, what do?
We go to Q1.
You go to Q1. So, if our start state, or if the state that we're reading is Q naught, and the input symbol that we're reading is epsilon, we just go to Q1. No choice about it. Right? And then finally, if we're at the start state, the new start state, Q naught, and we read some symbol that's not epsilon, like a 0, what do?
You die.
You crash, you die. So then we go to the empty state if you're in our new start state and you're not reading the epsilon transition. You're only allowed to transition on an epsilon from the start state.
So if you have 2 patterns and you're duplicating it over again, and there's no epsilon between them, you still lose even though you have the pattern doubled because of that Q naught?
Well, remember, you accept a string if there's any way to accept a string. And the string, pretend that this was recognizing zeros and ones, the string 0, 0, 1, epsilon 0, 1 is identical with the string 0, 0, 1, 0, 1. Inserting an epsilon in there doesn't change anything.
Yeah, but if there wasn't an epsilon.
So if there's some configuration of epsilons I could sprinkle in the string to make it go through my machine and accept, it accepts that string. If that's how you want to think about it.
Because even if the set of strings were a repeat within themselves, it would still work, is kind of what I'm seeing. So if it was 1, 0, 1, 0, 1, 0, and then it was on repeat.
Putting these epsilons in here is very logically equivalent to multiplying a number by 1. If you got some expression and you multiply it by 1, you can plug in as many times 1s as you want, and it doesn't change your string, or it doesn't change your number. Similarly, you can concatenate with as many epsilons as you want in whatever order you want, and it's not going to change your string. And so you can put all the epsilons in your string you want, just to make it go through your transition function fine. You didn't change the string. It's still an identical string, which means the machine can accept it. You just picked a different way to write it.
But if you don't have any epsilons, then it wouldn't go through the string, right? It wouldn't go through the machine, right?
Just rewrite the string so that it has the epsilons in the order that you want.
It's an infinite amount of epsilon between every letter, essentially, or symbol.
Right. You can concatenate with epsilon, doesn't change the string. So it's still an identical string. You didn't really change it. You just wrote it different. It's the same way that this is identical to this. I just wrote it two different ways. And maybe one of these is easier for you to reason about. Okay.
Or 12 times 1 is...
It's like me saying, I build a machine that only recognizes numbers that have odd factors. And you look at 12 and you say, no odd factor. Well, it does if you would have written it like this. It's just we didn't make it explicit. Kind of. I don't know if I'm helping or hurting.
Technically, they all have 1, which is odd, but
Odd factors, well, as 1, but I didn't write it as 1 times something. I just wrote it as 12.
but 1 is a factor of 12.
That's his point.
Right. The same way that some string epsilon is the same as that string.
I see what you're saying. I'm confused how that machine accepts the empty string though. Is it just because nothing is read, so nothing happens at all?
Yeah, if we read nothing, then the string we read is the empty string.
Okay. All right.
Okay.
If you read nothing, does your function still put you in?
Reading nothing, I could end up here, or possibly other states. And it's trying everything in parallel.
Right. So doesn't that mean that? Oh, no, it doesn't. Okay.
Okay. So we explained the transition function here, and then obviously define our new machine, n, which has the same states that our first machine had that we started with, union together with the state we added. This was the only state we added. So take our existing states and the state we added, union them together. There's our new states. Our language stays the same. We defined our new delta right here. Q0 is now our start state rather than Q1. F1, our accept states are still the exact same, except for we add Q0 as an accept state. And that's our new machine, recognizing it. And since we can build a machine recognizing it, then it's regular. Good? So we showed that the 3 important operations, the regular operations we call them, are all closed on the regular languages. That was the crucial part. Now, almost any operation you could come up with for regular languages, it turns out regular languages are closed on. These just happen to be the 3 that we're most interested in. So we'll do a couple other side proofs of things that are also, the regular languages are also closed under, because why not? Make sense? All right, so another one. We already talked about this one, so I decided to just throw it up there since we already said it before. If A is regular, so is A complement. So let's go back now and just think about a DFA. We'll just even draw a picture of a simple DFA really quick. Let's do a DFA recognizing, I don't know, even number of zeros. Pretty basic one. So here's our machine. Call that Q0. We have some other state here, Q1. Q0 is our accept state because we start out reading 0 zeros. If we read a 0, we transfer over here. If we read a 0, we transfer over here. If we read a 1, we stay. If we read a 1, we stay. Right? So here's the machine that recognizes all the binary strings that have an even number of zeros. How would we recognize now the complement? All the strings that don't have an even number of zeros. You just toggle your accept states. You make everything that was an accept state before not an accept state. And you make everything that wasn't an accept state an accept state. Make sense? And that's all you have to do for it. So let M1 be the DFA, recognizing A, then we create some new machine M, still going to be a DFA, recognizing the complement. The only thing we change, notice that they're identical, the only thing we change is the accept states. This one's accept states was F1, so this one's accept states is going to be Q minus F1. All the states that aren't accept states. Make sense? And so the complement is closed on the regular languages. Okay, let's do another one. If A1 and A2 are regular, so is A1. I lost the word. Intersect, thank you. So is A1 intersected with A2. And this one we're going to prove using one of those theorems we proved way back. It was the first theorem we proved in the class, I think, which was De Morgan's for sets. For those of you who know De Morgan's, those of you who don't, we'll remind you. So let A1 and A2 be regular languages. Observe that, here's what we proved earlier in the class. The complement of A1 intersected with A2 is equal to the complement of A union the complement of A1 union the complement of A2. Now you're looking at that and you're saying, holy smokes, how was I ever supposed to remember or recognize that? And it's just using De Morgan's for exactly how we distribute knots. So let me write some logic for you. If you have not alpha and beta, that's logically equivalent to, how do we distribute the knot? It becomes not alpha or not beta, right? Not alpha or not beta. Similarly, if we have not alpha or beta, that's logically equivalent to not alpha and not beta, right?
Yep.
These complements function exactly like knots, intersect functions exactly like and union functions exactly like or. If you remember the set definitions for each of those, their definitions came back to not and or. It's exactly where their definitions came from. Just write one of them out really quickly to remind you. A union B, by definition, is equal to the set of all x such that x is in A or x is in B. Notice A union B is implicitly oring two propositions together. So a union is an or. So not A1 and A2 is the same thing as not A1 or not A2. And that's how you can easily see and recognize those things. It just comes from the logic, as everything does. So you good with this line? Okay. So then, if I double knot something, what have I done to it? Nothing. In other words, the complement of a set just gets you back where you started. Right? So now, A1 intersect A2 is the same thing as the complement of A1 intersect A2, right? But now, if we just ignore the top line and just look at the bottom line, the complement of A1 intersect A2, this portion of it, is equal to this thing. So that is equal to that. In other words, if I put a line up here, I have to put a line up there. And that's what that's saying. The knot of this is the same as the knot of that. You with me? Now, you might look at that expression and say, well, how does that help us? What do we have here now?
A union.
We have a union and complements. It's just a bunch of complements and unions. Right? And if I take a regular language and I complement it, what's the language?
Regular.
And if I union it, what's the language? And so an intersection can be thought of as just doing a bunch of complements and unions. And so you're still regular. So then A1 intersect A2 is regular since union and complement are closed on regular languages. So that one we kind of got for free from doing the other two.
Is there a way to spell that out completely? Like if you didn't already have the fact that union and complement are close?
Could I have designed a machine to accept that? Yes, I could have.
Okay.
But why go through all that work? all we really care about with these machines is showing languages are regular. That's fundamentally what we're interested in. Showing things are regular, and we're coming up with a bunch of different ways to show languages are regular. Because classifying a language and solving a problem, kind of close to the same thing.
Is it really complicated to design a machine that accepts the intersect of those two? Like, could you show us like we did with the union?
It's not as straightforward.
Okay.
But the intuition for it is pretty straightforward, which is, if I were to actually design it, I'd use a DFA, not an NFA. And I'd have it running both machines in parallel, and then only accept on the intersection of their accepts.
Alright.
But no, I don't see an obvious way with NFAs to just see it and do it. NFAs are great with ORs, not so much with ANDs. Anyways, and then we already have that conversation. Okay. And there's a lot of other operations we could come up with regular languages and show that regular languages are closed under those operations. We've done enough. Another example of one that's not too bad is like showing if you reverse all the strings in the language, it's still a regular language. I don't know, there's a bunch. Okay, so now let's briefly talk about not a regular language. So it seems like everything's a regular language. Are there languages that aren't regular? And if they're not regular, how on earth do we know that they're not regular? Right? So we'll have this brief conversation now, and then we'll have this conversation again because the way we prove languages aren't regular, the ability to do that is a huge part of this class. We have to use something called a pumping limit. So introduce you to the logic of it early before we actually prove it. The whole section will be on how exactly we prove these things. But let's just walk you through the logic. So first off, let's think about the language. 0 to the n, 1 to the n, where n is some natural number. And remember that those aren't exponents. That's repeating the operation the same amount of times. So what is this language? That would be like the empty string, the string 0, 1, the string 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, etc. All right, how can we build a machine that recognizes this language?
You have to essentially be able to go through and have it accept and have it continue with all the zeros until it reaches a 1 and then switch and check to make sure it has ones only after that.
All right, so we might have something like, okay, here we are starting, and we start and accept in the same place. If we read a 0, then we have to read a 1 to get back, right? If we read a 0, 0, well, then we have to come off, read a 1, and then read another 1 to get back.
Yeah.
And if we read another 0, so we can see how we can do this with an infinite state machine.
But it would have to grow infinitely or variably.
But is there any way we can do this with a finite number of states?
No.
Well, it appeals to our intuition that we can't, but how on earth can we say that we can't? How do we prove that we
You
can't?
have to have as many states as there are natural numbers.
Well, if we construct it this way, maybe we're being stupid. Maybe this is a terrible approach.
There's a repeater that will somehow find a pattern. But you're right, there's one piece, I don't know.
So how could I possibly convince you that of all the infinite machines out there that you could possibly come up with, none of them will solve this problem?
Infinite? Oh, that might be.
Yeah, you can make it as arbitrarily large as you want.
Well, you could always try finding like a contradiction and say that it is possible.
Right, so we have to use the notion of a proof by contradiction. And I'm not going to give you the general way that we prove these things. I'm just going to walk you through an argument that you might have. So we're going to pretend something, and we're going to pretend that Levi goes home and he actually solves this problem. Or at least he thinks he does. And so he's got his machine, and he's convinced that his machine solves the problem. I'm going to ask Levi some basic questions about his machine. And I'm going to demonstrate to Levi that actually his machine doesn't solve the problem. You with me? And that will give you the high-level notion of how these types of arguments go. We'll do this again when we actually get to these arguments. I just want to expose it to you a few times because this exact type of argument is going to come up a lot in this class. So Levi goes home, he builds his machine, he comes back and he tells me, and he says he has his machine. I ask Levi a question, I say, how many states are in your machine? Give me some number.
27.
27. He says 27 states are in his machine, he counts them. If he has some machine that recognizes this thing, it's got to have a finite number of states. He gives me that. And I say, okay, your machine has to recognize all these strings, so it has to recognize this string, 0 to 27, 1 to 27, right?
Sure.
Everyone understands that. His machine would have to recognize this, right? And his machine has 27 states. Well, I also say, in reading the zeros, since you have to move one state, we'll assume that we've converted to DFA. When we convert to DFA, it has 27. So in order for him to read 27 input symbols, he would have had to transition through 28 states.
To count that you actually have 27, I see that.
So in other words,
Oh yeah, yeah. So if you were to jump,
if we start here and we read 2 symbols, we would have had to go through at least 3 states.
if you were to bounce back,
If
and
we
forth,
read 3 symbols, we have to go through at least 4 states. So if Levi reads the first part of this string, which has 27 symbols, he has to go through at least 28 states.
But some of those states could be the same.
Yeah, some of them could be the same. So the point is he has a repeating state reading this 0.
Yeah.
Somewhere along the way, the machine, so the machine's going along, it's here, his machine goes along, dot, dot, dot. Eventually we get to some state here, and it goes along after that, dot, dot, dot. And it gets to some state that loops back. And then
Loops to itself.
continues on, dot, dot, dot. And then we ultimately get to the accept.
but it can never repeat because it would lose count of how many zeros.
Well, we don't want an argument that's specific to this language.
Okay.
Too specific to it. So far, we know that his machine, somewhere along the way, we had to go back to the state that we already visited.
Which could include itself.
It eventually has to go back to the same state twice. There had to be some loop. This loop could have had other states in it. But we eventually have to loop back to some state again. Oh, you're saying it could have been a self loop like that?
Yeah.
Yes. Could have been a self loop like that where we only read one symbol, or it could have been a bigger loop where you have to read a bunch of symbols to go on the loop. Either way, there has to be some loop in there. So I tell Levi, I say, Levi, how many symbols do you read before you get to your first repeating state?
It has to be less than 27,
Right. Give me the number. You count it. For this string, you count it, and you give me the number. 14?
Sure.
14. So if we read 14 symbols, then we get to the point where we're at his loop. And now I say, how many symbols did we read going through the loop?
2.
2. So we only read 2 zeros going through the loop. 14 and 2, which means how many zeros came after the loop? 11, right? And then we had 1 27 times. So we break up the string like this. So this was the symbols we read before the loop. These 2 zeros took us on the loop. We read 11 zeros after the loop, and then 27 ones and accepted, right? I say, well, Levi, if you accepted this string, then you will also, then I want you to try this string. Do 0, I'll write down here. Do 0 14 times, now do 0 2 times, but now someone give me any number, doesn't matter, 6. And then 0 11 times, and then 1 27 times. Look at this new string. And you'll also accept this new string. What's this new string going to do? He's going to go get to the point where it gets a loop. It's going to do his loop 6 times, and then continue on its merry way with the remaining part of the string.
Okay.
Notice that this, now, is not in your language. We have more zeros than ones.
Yes.
So your machine accepts a string that's not in the language. So this is not the language of your machine. Whatever the language of your machine is, it's not this language.
It could include that language.
It could include that string. It's not hard to create the machine that accepts everything.
Right.
So we can always get more than we want. That's trivial. As a general rule, the more you include, the easier it is to come up with the machine. The more restrictive it is, the harder it is. And so his machine does not accept the language he thought it did. And that's roughly the logic of it. If your machine accepts it, if we give your machine a big enough string, it eventually has to loop. And if we're clever, we can make it loop in such a way that it generates a string not in your language. That you were after. Okay. So that's the general idea there, and that's introducing you to a non-regular language. Good? And we'll have a lot more to say with that exact type of logic that we walked through. I just want you to see it a few times. Because it can be tricky when we write it out. You'll see that it has like 4 quantifiers in it. And doing a negation of 4 quantifiers gets ugly. Because it's a proof by contradiction. Anyways, we did that. Now we're over here. Completely switching gears now. New section, section 1.3. Which is now regular expressions. Good? You shifted gears. Ready to go?
Before we shift gears,
Okay.
I feel like I need a little bit of clarification.
All right.
There's just little pieces that I'm missing. One is in our theorem at the top of that third column. At the top. Yeah. I'm missing this step on how Q minus F makes it the common.
F is all the except states. Q is all the states.
All the states accepted by M1, right?
No, this is all the states in this machine. We're reconstructing the same machine. We're just changing the accept states.
So
Our new machine is identical to our start
So
machine.
your accept states are all the states that weren't accept states before. Okay. And
Exactly right.
star, just to make sure I'm clear on this, star is basically any combination of strings in that language possible.
Take the language,
Concatenated on top of each other.
pick a string in there, and then grab another language, take another string, concatenate it on, take another
As
string,
many
concatenate it on as many times as you want. You don't have to pick the same string over and over again. So if we were looking at the language AB, then AB star is literally all the strings we can make using the letters AB.
Right.
And you'll get more comfortable with that literally right here.
So on your note, why are we interested specifically in union, concatenation, and star?
Because we use them in regular expressions. Those are the ones we use in regular expressions.
You said almost all operations are close on regular languages.
Yeah, basically any operation you could come up with for a language, when you apply that operation to regular languages, chances are it generates a regular language. Don't ask me for an example of one that doesn't, because I don't have one.
So why are these three special?
Because they're the ones that we use to generate regular expressions.
Oh, okay. Oh, okay.
Okay, and you'll see how that ties into the stuff we just talked about, and why that was so crucial to do, in particularly those first 3 proofs. And we'll see all that. So, but before we do, let's first get comfortable with regular expressions and what exactly is a regular expression. Now you're used to algebraic expressions. Algebraic expressions, something like this. 4 plus 5 squared times 6. Takes a bunch of numbers, applies a bunch of operations to those numbers to ultimately spit out one number. A regular expression is going to do the same thing with languages. It's going to take a bunch of languages, apply some operations to the languages to ultimately spit out a language. Same thing. So, same way that we have 4 plus 5 squared times 6, that's some expression, algebraic expression. We could also have something like 4 times 5 plus 2. Now notice with algebraic expressions, sometimes we drop the times, and we don't bother writing that out. We're going to do something similar now with our regular expressions. So, let's look at our first regular expression. Here's an example of a regular expression. We have a language, which is 0 in it. We're going to keep these stupid symbols.
So that's not an alphabet, that's a language.
That's, yeah, it's a language. How's the best way to say this? Because we're also going to use regular expressions to generate languages. And so I don't want you to get confused by the components of a regular expression are going to be languages, but we're often going to talk about the language that the regular expression generates. The same way that this generates the number 35. When we use the word language, we're going to be typically talking about the ultimate language that comes out when it's all said and done.
I just wanted to clarify that your concatenating 0 and concatenating 1 are actually languages. Are not
Yeah, you can call them languages. But typically when I say, now looking at this language, we mean the language that comes out when you apply all the
Oh,
operations.
so the concatenating 0 isn't necessarily a language, but
It is a language,
it
but
is.
we'll never really talk about the language of concatenating 0 except for like right now.
Okay.
And then after that, when we say language, we typically mean what ultimately comes out. Kind of like when I say, now look at this number, I kind of mean when you evaluate the expression, even though each of those are numbers. Similar thing. Okay, so concatenating 0, union with concatenating 1, that gives you some new set, right? These are ultimately all set operations. And then we can also do 0 star. That gives us some new set. This gives us an infinite set. And then we can concatenate those two languages together, and once again, that gives us some other language. Right? So this is how we apply these regular expressions. Now, reading this can kind of turn into a nightmare, and reasoning about what strings this really generates, what language do we ultimately generate when it's all said and done, looking at all this kind of turns into a headache. And so we rewrite it like this. Rather than writing the concatenating 0, we just put a 0 there. Rather than the concatenating 1, we put the 1 there. And we don't bother writing concatenations unless we need them. The same way that we didn't bother writing times unless we need it. So this regular expression is the same as this. This is much preferred. And what are all the strings generated by this regular expression? What's the language of this regular expression? Are all the strings generated by this expression? It's all the strings that start with a 0 or a 1, followed by as many zeros as you want. It's much easier to reason about this than it is to reason about that nightmare. So we write it this way. So the string starts with a 0 or 1, and is followed by as many zeros as you want. Question, does this generate this string?
Yes.
So this string is in the resulting language.
Yes.
That's a 1 followed by no zeros. Perfectly valid. Or we could have this string, right? What about this one?
No.
0, 1, 0, 0, in case you can't read my writing. No, that's not generated by that. Okay? Let's go over a bunch of examples now, and you're just going to tell me how to write it. Oh, some notation. So if sigma is equal to 0, 1, if that's the alphabet we're talking about, then sigma star is shorthand for 0, 1, star, 0, 1, star, 0, 1, star, 0, 1. So basically, all the strings that can be generated with zeros or ones. So 0 or 1, and then do it again. You have your choice of 0 or 1, do it again. You have your choice of 0 or 1, do it again.
So sigma star is a language. Is a regular language.
Yeah. Sigma is a regular language, and sigma star is a regular language.
Sigma is an alphabet.
Right. We could also call it a language if we want to view those things as
Strings.
strings.
Oh.
What's the difference between a language and alphabet again?
Technically, they're both just finite sets.
But they're used differently, right?
Well, you just usually have an alphabet. When we say that this is the alphabet for this language, we're just promising that all the symbols in the strings in this set are in this other set over here. That's all we're saying. If you don't want to think about this as a language, that's fine. But this definitely, you do think about as a language.
Right. Do we use sigmas to, conventionally, do we use them as alphabets and languages?
When you see a sigma, we typically mean it for an alphabet. So when you see sigma star, that means now any string that could have been generated by the alphabet. And that's typically how we think about it. Okay, so now let's do some examples, write some regular expressions. Maybe I'll do the first one for you so that you can get a feel for this, and then you can do it from there. So we want to write all the binary strings that start with a 0. How can I write a regular expression that generates all the binary strings that start with a 0? I could do 0, and then after 0, we can do as many zeros or ones as we want, right? Now, it's tedious writing that. It turns out that this symbol right here is something that we want to write a lot. So the way that you would have actually seen this is 0, sigma, star. 0, and then anything you can generate with the alphabet after that. Starts with a 0. Okay, so how would we do, oh, yeah, how would we do ends with a 1?
So 0, sigma star, and then 1.
Sigma star followed by 1. Anything you can generate with our alphabet followed by a 1, that means it ends with a 1. All right, what about starts with a 0 or ends with a 1?
You just mix those two, basically.
Do what?
0, sigma star,
0, sigma star, 1, right?
but that's and.
Oh, that's and. Shoot.
So would you just OR the first two that you, or sorry, union?
Union. So we take that and we union it with sigma star 1. Here's all the strings that start with a 0. Here's all the strings that end with a 1. You union that together, you have all the strings that start with a 0 or end with a 1.
Why can't you write it the other way again?
So here's an example of a string that this generates. That is generated by this regular expression. Because it's generated by this thing.
Or ends. Okay, sorry. I thought for some reason I'm thinking and ends, but okay.
Okay. Good on that one? All right. Order of operations. You probably already figured it out. Let me rewrite this one explicitly. So that was really 0 concatenated with sigma star unioned with sigma star concatenated with 1. Order of operations. Which do we do first? I didn't apply the star to both 0 concatenated with sigma. I just applied the star to sigma. Right?
Yep.
Similarly, I didn't concatenate a 1 onto this whole thing. I concatenated the 1 just onto this thing. So there's an implied order of operations here. And the order is you do stars, then concatenations, then unions. Similar to when you're doing your algebraic expressions, first you do the exponent, then you do the multiplication, then you do the addition. So stars like exponents, concatenates like multiply, unions like add. So here, we are starring this sigma first, then we're concatenating this together. We're starring that, we're concatenating that together. Then finally, we're unioning this with this. Make sense? And you probably would have already guessed that, but in case you didn't, let's make it explicit. And you kind of just get used to it the more you work with these things. All right, so we played with some regular expressions. Now the natural question is, what is a regular expression, right? So let's get a precise definition for what a regular expression is. R is a regular expression if it is one of these 6 things.
Is that supposed to say def?
Yes. A dir. It's because my next symbol is an R. Okay. I'm guessing. Who knows? All right, R is a regular expression if it's one of these 6 things. First off, it's a regular expression if it's just a symbol from the alphabet by itself. So 0 by itself would have been a regular expression. 1 by itself would have been a regular expression. Good so far? Secondly, it's a regular expression if it's just the empty string. Good? Thirdly, remember these are shorthands, by the way. When we put A in a regular expression, we really mean the set containing A. When we put epsilon in a regular expression, we really mean the set containing epsilon.
So all regular expressions are sets.
Their components are sets.
So
They're
they-
composed of sets, putting sets together.
So they are a set.
Yes.
The full expression.
The regular operations are set operations. So the operations only make sense on sets.
Okay.
which is why we did a bunch with them before we got to regular expressions, so you keep track of that.
That's right.
Yes.
Well,
Not today we didn't. We did it before when we first introduced these. And we wrote out some sets explicitly applying each of these 3 operations. Not today. It's not written over there.
I know.
Okay.
I'm just thinking of automaton, how they are tuples and how that fit.
Well, we'll tie automatons into this whole picture later. And so now, it might not seem strange to you now that that the empty set is a valid regular expression. Just nothing in there.
Yeah, that's it.
Then the empty string,
The empty string is a list.
this, if we write this out explicitly,
They still,
Right.
still equal the same.
the list that contains nothing in it. Or for those of you used to programming, an empty string, no character in it. Same thing. Or the empty set. And now hopefully the empty set doesn't seem weird that we just threw that in there. So remember that these are always sets. Okay. So the regular expression, it can be one of these 3 things, or it can be a union of 2 things, where those 2 things are themselves regular expressions, or it can be a concatenation of 2 things, where those 2 things are themselves regular expressions, or it can be a starring of something where that thing itself is a regular expression. And so this is like a constructive definition. You can start with these things, and then you can start unioning and concatenating and starring these things, and it's still regular.
But not stuff like complement.
But what?
Not stuff like complementing themselves.
Yeah, complementing is not in a regular expression.
Is there a
Neither is
reason
intersecting.
why? It seems a little bit arbitrary. Like why?
Regular expressions are used a lot in programming, and you use them a lot to help you identify things, and they're just easy to reason about. And so they're just more useful operations. It's like, why are some operations more useful than others? It's the use cases.
So they basically said, here's a set of useful operations. Anything that uses only these is a regular expression.
It was more like there kept coming up these types of problems that we need to solve, and these 3 operations kept helping us do it really, really well. And so we came up with a restrictive type of expression to start talking about that only has those 3 operations to solve these types of problems. And a typical place it's used is like checking is something a valid email address. And you use a regular expression to check that.
Okay. It still seems kind of arbitrary, but
It's just because they were useful. And so they're used a lot in programming. They just happen to be useful for programming.
So there's no
It's the same way like with logic. Why do we use and or not, and we don't use the exclusive or the NAND?
well, you use them when you need to.
You use them when you need to, but as a general rule, we don't bother with them.
You also don't call and or not with regular operators.
But you could, and there'd be nothing wrong with that.
But like, why would you?
Well, just because if you want to talk about some subset of logical operations,
Okay.
and you say, whenever we're talking about these subsets, we promise that we'll only use these 3 things. And so we can develop a notation using those 3 things. So instead of having to use this, which is what we'd have to do if we restrict ourselves to sets, then we say, now in this context, you understand what something like this means, or something like this means. So it just enables us to,
Convenient.
yeah, it's all about convenience.
Okay.
All right. So these are basically our 3 fundamental components that we use for building regular expressions, and then take those and start unioning them or concatenating them or starring them together, and the result is still a regular expression. And you'll notice that all these regular expressions are ultimately these things. Remember that sigma star is just shorthand for this, so still doing it. Good?
In all regular expressions?
All regular expressions, by definition. They fundamentally are individual letters from your alphabet, or the empty string, or the empty set, or unions, concatenations, and stars of those things.
But it's not the 0 and 1 alphabet, is what you're saying.
It doesn't have to be the 0 and 1 alphabet. We typically use 0, 1. Could have used AB. It's just standard to use 0, 1. So that's what we use. Okay. Any questions on that definition? That definition makes sense to everyone? Regular expression. And it just so happens that regular expressions are logically equivalent to NFAs and DFAs. And so the languages that can be recognized by regular expressions are going to be themselves regular languages. And the remainder of this section, we'll do some exercises getting used to these really quick. But after that, the remainder of this section is just proving that fact. That, hey, this thing is really just as powerful as an NFA or a DFA. So now we have, after that, we'll have 3 different ways to check to see if a language is regular. And that's big picture where we're going.
Did you say for the rest of this lecture?
For the rest of the section of the book. That's what it's about. And so you see word machines over there. They're word machines that we'll get to. We'll only use them for a short period of time for that exact thing I said.
I don't know, it just seems obvious off of all the other theorems that we built up, like yeah, they're regular
Well,
languages.
We'll do some work and
Okay.
maybe it's obvious, maybe it's not. Okay, so let's do these exercises really quick. So we'll assume our alphabet is 0, 1. And you're just going to start telling me what these things are. So let's start with 1. We have 0 star, 1, 0 star. So this is a set of all strings where the string's what?
Starts with as many zeros as you want, and there's 1, and there's a bunch of zeros after it.
Give me an easier way to write it. Huh?
Is that saying that there's the same amount of zeros before and after?
No.
So
Any amount followed by a 1 followed by any amount of zeros. Could be no. You can have 100 zeros, a 1, 2 zeros. And that's
It's
it.
a natural number. 1, 0, 2, and other.
There has to be a 1. There's exactly 1, 1. So instead of all W's with 1, 1. Exactly 1, 1.
Yeah. Oh. Because there could be no zeros.
Yeah.
Right. There could be no zeros. There could be a trillion zeros, but it has to have 1, 1. Okay. Next language. Sigma star, 1, sigma star.
It's at least one.
This is at least 1, 1. You got any number of symbols, zeros or ones, followed by 1, followed by any number of symbols, zeros or 1. This is a set of all strings that have at least 1, 1. This is exactly 1, 1. This is at least 1, 1. Right? Okay. What's this? Any number of symbols, 0, 0, 1, any number of symbols.
It has a substring 0, 0, 1.
Contains substring 0, 0, 1. Good. All right. Let's see that monster.
Anytime it has a 0, it has to be followed by 2 ones.
Anytime it has a 0, it has to be followed by 2 1s.
Not
Who
necessarily,
buys
because
that?
There doesn't have to be a 1. It has to just have, well,
Not quite.
Is that star that's next to the one inside the
So there's a star next to this one. This star is being applied to this one. This star is being applied to the whole operation here. And then that star is being applied there.
Has to
That
be
star's
followed by
not
at least
applied to
1,
the
1.
zero of one before.
This star only applies to this one. It does not apply to this one. It does not apply to this one. Or the 0.
So a 0 has to be followed by at least 1, 1.
Every 0 is followed by at least 1, 1. Is what that is saying in a mouthful. Let's write out a string generated by this really quick, just to see it. So we have 1 star here, so I can start by doing a couple 1s. 1, 1, then we have this thing, so then I have a 0, a 1, then I can have as many 1s as I want. Put a couple more 1s there. And then star. I can repeat what's in the parentheses again if I want. Let's repeat what's in the parentheses again. So that's a 0, and then a 1, and then as many 1s as I want. I don't want any 1s this time. Star means I can be done or I can repeat what's in the parentheses. I'll repeat what's in the parentheses one more time. 0, 1, a few more 1s, and we'll call it good. There's an example of the string.
So-
Every 0 is followed by at least 1, 1. Notice that this is also a valid string. 0, 1, 0, 1, 0, 1. Don't do this any times. Then do 0, 1. Don't do this any times. Repeat 0, 1, none. 0, 1, and be done. Good? this was every 0 followed by a 1. Okay. Now let's try one where you tell me the regular expression's right. I want all the strings of even length.
It would be a parentheses, then inside there, sigma concatenated with sigma, and then just a star outside, I think.
Would that mean that sigma would have to be the same?
Perfect. You can have a 0 or a 1 together with a 0 or a 1, and then repeat as many times as you want.
So the sigma,
This is the same thing as, let's just write it this way in case it helps. 0 union 1 concatenated with 0 union 1 star. You can have a 0 or 1 concatenated with a 0 or a 1. Do as many times as you want. You can do it 0 times, you can do it 100 times. Good? Alright. And then length, a multiple of 3. I think you guys already get that one now. I wasn't going to bother with this one if you figured out to do it this way rather than trying to think about that way. So that's just 2 sigmas in a row. Sorry. Right? Any alphabet symbol, any alphabet symbol, any alphabet symbol. Do as many times as you want.
is your notation where you can.
And that was supposed to be length multiple of 3. I don't know if I actually read it.
So when you
Sorry.
have an alphabet symbol to the power of something, can you use that in any of this? Because then you could go sigma to the 3 star. Does that work?
I think people could infer from context what you meant.
So is it not conventional to do that? Or?
Well, we haven't been doing that because remember these are sets. We've been doing that for symbols. We haven't been doing that for sets.
But sigma is just as simple.
Because you're saying to do something like, when I see 0 to the 3 in a regular expression, this does not mean the string 0, 0, 0. This is the way we typically use it. 0 to the 3 means 0, 0, 0. We do not typically mean 0 to the 3 to mean
Yeah.
Although that would work. That would work.
it would work. It would give you this. So I'm saying I think people could infer from context what you meant. So I'm not sure there's necessarily a problem with it. I don't think that's used in the book.
That is so cool.
But you could use that up when you were writing it in terms of W, right? In your cycle notation. No, you couldn't. That's the same concept.
Yeah, just
Okay.
sometimes it's good to hold back just to avoid confusion, even though there's a perfectly reasonable way to interpret it. So
Kind of making me think of math differently.
well, that's good. Everything we're doing here is math.
Yeah. I never thought about it this way.
All right, that's the next one. 0, 1, union 1, 0. What's that?
There's only 2 strings that make sense, right? 0, 1, 0, 1, 0.
0, 1, 1, 0. It's just a set. This is a set containing 0 concatenated with the set containing 1. And this is a set containing 1 concatenated with the set containing 0. Union those 2 sets together, and that's what you got.
Okay.
Just those 2 strings.
Right.
Can be weird. 1 second you're thinking about those as symbols, the next you're thinking about as sets.
Yeah.
It's weird going back and forth, which is why I decided to throw that one in there. Remind you.
These are sets, not symbols.
Over here, we're talking about sets. Over here, they're symbols.
Yeah.
Yeah. Over here, we're talking about regular expressions. Over here, we're talking about strings. Sets of strings. Okay. Let's try this one. That's a 1, by the way. We're not doing like an absolute value symbol around that. In case that looked weird. Look at this one. What are the strings?
It's Well, I'm trying to find a simple way to describe it, because it's a 0 with a bunch of stuff in between and another 0. But
Or
0 sandwich or 1 sandwich?
That's a power
Basically.
server.
0 sandwich or a 1 sandwich.
How he's like-
Or it starts and ends with the same symbol.
Okay, see, that's what I was looking for.
Same symbol.
Starts and ends, same symbol. You get it.
We don't use the power set in regular expressions, right? 'Cause-
No.
Okay, that's
No,
what I
no,
thought
no.
that was. Okay,
We only use these 3 operations. Union, concatenation, and star. Power set is another operation on sets. We don't use that. Okay. So now, we can also do a little bit of algebra with these things. So if you were to see something like 0 union empty string concatenated with 1 star, we can distribute this exactly the way you would expect. And we can distribute it exactly like that. Concatenate that with that, concatenate that with that. In other words, we can concatenate over unions. The same way you can multiply over addition. Right? If you were to see 1 plus 2
Right.
times 3, that's the same thing as 3 times 1 plus 3 times 2. And if it would have been a 3 squared, we could put the square there and the square there.
Right.
So in simplifying these expressions, those same types of distributions work. So 0 union epsilon concatenated with 1 star is the same as, because that might be a little bit hard to reason about, but once we distribute the 1 star through, 0 1 star union epsilon 1 star, now that becomes a little bit easier to think about. Right? The empty string concatenated with strings of 1s still just gives you strings of 1s, so you can do some simplifying there. Concatenating with the empty string is a lot like multiplying by 1 in algebra. Doesn't change your language. Take your language. Now, every string in the language, I want you to start it with an epsilon. What did you change? Nothing.
So
That's what we're doing here.
Is that only when you union with epsilon, or is that when you union with any symbol?
That wasn't a union, that's a concatenation. We just didn't write it.
I mean on the other side here.
Going from here to here, all I did was simplify this term.
What I mean is, does that property apply for any symbol, right? Because 0 union with epsilon is just 0, but you could go 0 union with anything.
Whoa, no. Union, different beast. Let's write it out explicitly. 0 union
Okay.
epsilon is equal to the set containing 0 and epsilon.
Right.
If we did 0 concatenate with epsilon, now it's just a set containing 0.
Okay.
These get tricky. So epsilon here is acting a lot like 1, where concatenation is acting like times. Now, none of our regular expressions so far have the empty set, but unioning with the empty set is like adding 0.
Right.
So the empty set acts a lot like 0. And so if you would have seen 0 union the empty set in a regular expression, that means the set containing 0 unioned with the empty set. And what's everything that's in here or here?
It's actually containing 0. So, I mean, that answers my original question, but I was just asking if you could put any symbol where epsilon was on the left side of that equation. Not bad. Yes, if you could use any other symbol, it doesn't have to be epsilon.
Oh, I could put a 1 there.
Yeah.
Nothing wrong with a 1 there. Oh, yeah. I can union with anything. Look back at your definition. Is that by itself a regular expression? Yes. Is that by itself a regular expression? Yes. Unioning regular expressions? Still regular. Concatenated with a 1? Yes. A 1 star? Yes. So, yeah.
So, just so I understand that probably, if it's saying there's a repeat of 0 and 1, wait, no, only repeating 1.
So this is This is your first symbol can be 0 with as many ones as you want. So it's either 0 with as many ones as you want or just a string of ones. So if there's a 0, it's only the first symbol.
Okay,
That's what that's saying.
that makes sense.
But let me write out a little bit of algebra to the side and then write some stuff with our regular expressions and see some parallels here. Actually, I think I have it down here. Doesn't matter. I'll just write this anyways, just to help give you intuition for some stuff. When I say x plus 0 in algebra, what's that always equal to?
X.
X. When I say x times 1 in algebra, what's that always equal to? X. When I say x times 0 in algebra, what's that always equal to? 0. Right? Similarly, if I have any regular expression and I union it with the empty set, that just gives me my regular expression. If I have any regular expression and I concatenate it with epsilon, that just gives me back my same regular expression. If I have any regular expression and I concatenate it with the empty set, that gives me the empty set. Regular expression, ultimately this generates some language, right?
Yeah.
Take any language, now take every string in that language and concatenate it with every string in that language.
You should get R, shouldn't you?
No, that is this. When I concatenate nothing onto each of those strings,
Okay.
then we're good. I have nothing to concatenate with. It starts with things from here and ends with things from here.
And nothing ends with these two, right? Is that what you're saying?
And there's nothing with it to end. If it ends in an empty string, that's what this is.
Right. So it has nothing with which to end, so there's nothing there.
Right, you can't concatenate with the empty set. Concatenating with the empty set, well, you can, it just gives you the empty set. Here are all the strings whose first half is in here and whose second half is in here.
Right. Didn't think about that.
I'm still not getting that.
You could just draw a simple example of a regular language and maybe set and how they would concatenate.
Well, yeah, I don't know how else to do it. So, the set just containing 0. If we concatenate this with the empty set, or the empty string, I mean, then we take things in here, concatenate them together, and stick it in the set over here,
0 makes sense.
which will just be 0. Okay, next. This is a set of everything we get, and I'm going to put inside this set all the things we get when we concatenate from here. Pick something in here, and here's a better way to say it. Take everything in here
Yes.
and everything in here and concatenate them together.
So it'll be 0.
No, it's nothing.
I don't understand.
You can't concatenate with nothing. Concatenation takes two things.
What was it, area?
It's like if I say, take all the numbers in here and multiply them with all the numbers in here.
I know that.
You can't do it. There's no number to multiply with. Multiply is a binary operation. I need two numbers.
Right.
It's not just magically sticking a 2. That's multiplying by 1. You still multiply by something. You can't just magically stick a 0 over there. That's concatenating with the empty string.
So why does
You can't just...
why does epsilon get to be a number?
Why is epsilon going to be a number?
Yeah, why can that count if it's literally the same thing as?
It's not though.
It's not the same thing as the empty set.
Because it's a
The
string.
empty set and empty string are very different things. The empty string is still a string. It's a string that has no characters.
Okay.
Sorry, young program.
But in the context of set theory, it's just a list.
I get that.
They're all lists.
Okay, let's write it out as, there we go. We'll write it out as lists. Let's get back down to the nitty gritty. Writing these things out with their very basic math notations. All right, this list contains a 0, and that's it. And we're going to concatenate that with we're going to take all the lists in each of these sets and combine them together, and the resulting list we stick in there. Take all the lists, combine them, And the result goes in here. Okay, now try this one. Take all the lists in both these sets and combine them.
It's because I can't combine them?
There isn't a list.
So because I can't combine them,
It's because you can't get a list
It's like that.
to start by combining.
Oculus truth, kind
it's almost like it's so,
It's like you're trying to do a zip function
okay, hold on.
where you don't have an element on the right-hand
That
side.
might be a way to think of it, isn't it? Well, I guess, I mean, it kind of seems, I can see how it would air out logically. It just, I mean, I know you're right. I just,
We combine together all the lists in both sets. There is no list in this
so
set.
if something, there is no list, then it just destroys the other list or
It
something.
doesn't destroy it. We just don't have another list to combine it to, so it doesn't show up in the result.
In a way, we kind of just decided though.
of. Your final result is only the lists that you get from.
This is all the lists that you can get from combining all the lists in these two sets together.
Okay.
It has to be a combination of two lists to get over here.
All right, it's starting to make sense.
Okay.
I'm starting to see what you're saying. Cool.
Awesome. This is very confusing. Empty string, empty set, two very different things. In regular expressions, the empty set acts a lot like 0, and the empty string acts a lot like 1.
That's interesting.
Okay, so
And
now
union acts a lot like add, and concatenation acts a lot like multiply.
so these sets could have multiple strings in that set, and you're supposed to concat all of them, and then because there isn't.
Everything, every possible combination ends up in the result. And we did some examples of that, not last week, but the week before.
Is it the power set concept?
No, the power set is a set of all possible subsets. We wrote out explicitly these operations. You can go back and watch the lecture when we first introduced those, so not last lecture, but the lecture before. And we go through, just thinking about the sets, a bunch of examples of these three operations to try and get you comfortable with this.
Well, I'm just saying, in your set, you could have multiple lists, correct? So you could have a list of.
Yeah, we were keeping it simple. I could have had, let's do one explicitly. I'm not going to put the parentheses anymore, so.
That'll make a lot of sense once I see that.
I won't write them all, but it's equal to 0a, 0b, 1a, 1b, etc.
Yep. And because there's just nothing to, okay, it's now making perfect sense.
Yeah, you can't combine with the empty string. You got to combine with nothing.
But, yeah, well, if you're trying to compare a whole bunch of things and there's nothing to compare, I can see that there's no results to the
Right.
comparison. I get that.
Right.
Thank you.
Oh, that's exactly how I think about it. Think about nulling and programming. Try to concatenate null with a string. Not an empty string. Concatenate null with a string. You can't. It's not a string.
Yeah, well, instead of saying, get me all the combinations, and there isn't any combinations to give, yeah, that makes sense.
Okay.
Well, I think the confusion was that if you did something like that in programming, you get a syntax error, right?
Depends what language you
Yeah, it
use.
depends on
If it's
the
JavaScript, it might do undefined or.
In this case, it comes out with an actual result. It's not an error. It's not that you can't do it. It's just,
No, if you try to force it to give something, that's where you get the error.
yeah.
Right.
Yeah,
Okay.
put error out, somehow.
Anyways, moving on. Let's look at this one now. Yeah, we didn't do this one yet. So 0 union epsilon concatenated with 1 union epsilon. What are all the strings we can get?
There's 0, 1. There's one string we could get.
0, 1, like that.
Then
Yeah.
0 epsilon.
Well,
0 epsilon.
And then epsilon 1.
Epsilon 1.
Just epsilon.
And then epsilon epsilon. Which is just the empty string.
Just, I have to finish my train of thought, so just bear with me a second. If I was to put that in code, it would be a for each loop of the first set, with a for each loop, and inside of that for each loop, and then my logic to create the next list. But because the for each loop inside the for each loop would never loop, it would
You can
never
think about it that
create
way.
something in there.
Right.
Now it's making perfect sense.
Okay. Next one. One star concatenated with the empty set.
We just
The
set
empty
up
set.
empty set.
Empty set. Take all the strings generated by that, concatenate them with this, you get nothing. Same as multiplying by 0. Right?
Also the
Empty set star.
It seems like it'd be the empty set. Is it? Unless it's undefined. But it seems like it'd be the empty set.
We can generate the empty string with that.
Why? Stop.
Oh.
Star can always generate the empty string.
So infinite zero
Period.
is 1.
Okay, so I feel like I need to see the definition of star again. Oh, I know the definition of star. Okay, I got you. We're good.
Just because it's.
If we choose to use the characters from this set no times in generating our string, we generate the empty string. Okay? And so, sorry, this is the set it generates as a regular expression. If you were simplifying, you could replace that with just epsilon.
Right.
So if we were still writing a regular expression, it's that, but remember in regular expressions, epsilon is shorthand for the set containing epsilon. Same way that zeros were shorthands for sets containing
It seems
zeros.
like the shorthand really just means.
So it's just a simplification.
Couldn't that still be the empty set too?
No, that can't be the empty set. That can
Like
only
one-
be the empty string.
What if you do like one empty set repeated? I thought we got the empty string because we did 0 of the empty set and got the empty string.
Star is, so here is our empty set, right? When you star it, that is equal to the set of all the strings now we can get using the characters in here as many times as we want. And since the definition starts by already constructing a set, and then we have our empty string is the only string that we can construct, just give me a second to take the empty string. If I would have said A star, now that has the empty string in there, that has A, that has AA, etc. If I decide to use what's in here 0 times, it's this in generating my string.
Oh, I kind of see what you're saying.
Okay.
The empty string is a subset.
So the empty string is always generated by a star.
Yeah.
You can always get the star by using the set no times to generate it. That one's, I think that this is probably the least intuitive thing.
Yeah.
Outside of that, I think you're good. Because we don't really have like a algebraic equivalent of that. I guess some people sometimes say like 0 to 0 to 1.
Yeah,
That's like something like it. Probably a bad idea to even bring that up. Okay. So anything starred always generates at least the empty string. Just remember that, and then this you should be okay with. And then each of these we already said. Let's go over each of them again, just to remind ourselves. Any regular expression union with the empty set just gives you back that same regular expression. Union with the empty set doesn't change anything. Regular expression union with the empty string gives you, huh?
Gives you just that. Well, it gives you.
It gives you the regular expression union with the empty string. You just
Yeah.
have to make sure you include that string in there,
Yeah.
right? So, no weird elimination thing. Any regular expression concatenated with the empty string gives you
Just the regular.
just that same regular expression again.
Yeah.
Any regular expression concatenated with the empty set gives you
The empty set.
empty set. What if we concatenate with the empty set star? Then what does it give you?
Then it gives you R.
Then it gives you R. Because the empty set star is the empty string. That's the weird one. Get rid of the star. Now that's the empty set.
Yep.
Okay.
Weird stuff, but
Yeah, no, that
that's
makes
what it is. So that is a bunch of examples with regular expressions. We can do the first proof and then we'll hold off for the second part until next week. that will be a good breaking point, because it will tie back to all the stuff we've done earlier today. So we'll just do this theorem and then we'll call it good for today. Okay. So this theorem is now proving that any language generated by a regular language is regular.
Okay.
You with me? If a regular expression generates a language, it's a regular language. That's what we're proving.
What do you mean generates? Does it have to use?
When you evaluate the expression,
Does it
then
have
it's
to
a language
use
when it's all said and
regular
done.
Operations.
Yes. A regular expression is defined right here.
Oh,
Which
gotcha.
is one of these.
Oh, sorry. Yeah.
When you apply all the operations to the expression, when it's all said and done, you have a language. Same way when you apply the operations to the numbers, when it's all said and done, you have a number. So we're showing that that's what I mean by generates. We'll say if we were to evaluate the regular expression, the language that you're left with, we'll call it the language it generates. And so we're going to show that whatever language is generated, if a language is generated by a regular expression, then it's a regular language. Next week we'll prove the converse. If a language is regular, then it can be generated by a regular expression. The converse is harder. So we'll prove it the easy direction first. So if R is a regular expression, the language it generates is a regular language. That's what we're proving. And we'll be using proofs that we did earlier today. So let R be, Regex is short for a regular expression. Let R be a regular expression, and observe that there are 6 cases for any regular expression. Listed right here in the definition. For each of those cases, if we can find the equivalent NFA for it, that does the exact same thing, then we've shown that every regular expression can be converted to an NFA, which is what we're going to do. So if our regular expression is just the input symbol A, if it's case 1 over there, then notice here's the NFA that recognizes that symbol. Right? If our regular expression is just the empty string, notice here's the NFA that recognizes the empty string. It just accepts, and then if you give it any input, it crashes. So it only accepts the empty string. If our input symbol is the empty set, or if our regular expression is the empty set, here's the NFA that accepts that. The NFA that accepts nothing. It has no accept states. This NFA doesn't accept anything.
And how does it recognize the empty set?
What's the language it recognizes? What's the set of all strings that this thing accepts?
Oh, when you die.
The empty set.
So
The empty set. Every string makes it die. So here's the set of all the strings it generates. It accepts.
Gotcha.
Good?
So that could be more elaborated, have more sets coming off it, but if there's no finished states, then always.
Yeah, this is just a NFA that recognizes each of these. There's an infinite number of NFAs we could have chosen for each of these. You can blow it up with a bunch of nonsense as you want. Right? You can have components that aren't even connected. Okay, so that is for the first 3 cases. Now, for the last 3 cases, we have already shown how to create NFAs that recognize the union of 2 NFAs, the concatenation of 2 NFAs, or the storing of an NFA. Those were the first 3 proofs we did today. I showed you how to union 2 NFAs together. I showed you how to concatenate 2 NFAs together. And given an NFA, I showed you how to store it. Right? So here's the 3 NFAs for the first 3 parts of this definition. I've already given you the NFAs for the bottom 3 parts of that definition. And therefore, for any regular language has, or any regular expression has an equivalent NFA. Right? If the regular expression has an A in it, you start with that NFA. If it has an A union A, you take 2 of those and you union them together exactly how we showed you over there. Etc. And so that's how you build the equivalent NFA. So, therefore, the language of R is regular, because there's an NFA that can recognize the exact same language as that NFA, or as that regular expression. Now, notice that the way that we construct it from a regular expression is very systematic. We have to follow the rules over there over and over and over again. So I'm going to do one example with this string, and then we'll be done. So let's come up with the NFA that recognizes this thing. And we're not going to come up with the simplest one that comes up with it. We're going to come up with the one that does it, following the exact 3 rules I listed over here, and the exact 3 rules I listed in our terms over there. You with me? So we have an A and a B. So I need a NFA that recognizes a string A. So let's come up with that NFA. Right? Now I need one that recognizes a string B, and then I need to concatenate them together. So here's one that recognizes a string B. Here's its start state. Recognizes B. There it is. Here's A, here's B. Now I've got to concatenate them together. And I've got to concatenate them together exactly how we said over there. The way we said to do that over there was erase the accept state of the first one and create an epsilon transition to the start state of your second one. So I gave us this. Now I need a machine that recognizes just A. That's over here. So here's A concatenate B, here's A. Now we need to union them together. To union them together, we create a new start state, and we create epsilon transitions, like that. There's a union of them. And now I need to start. To start, we said add a new start state, make it also an accept state, so this is now our start state, also an accept state. Make an epsilon transition to the previous start state, and then create epsilon arrows from the previous accept states to there. Epsilon, epsilon. This machine's way bigger than it needs to be, but the point is, just following the 6 rules we laid out, I now know how to convert every regular expression to an equivalent NFA. Just following those 6 rules. Make sense? And so, that's our proof. So, next time we'll prove the converse, and we'll call it quits there. Do we have any questions before we call it quits for the day?
Yeah.
Go ahead.
So your proof basically said that a regular expression generates a regular language because NFA can recognize the language it generates. Is it incorrect to say that it's also generates regular language because all the operations used are closed on regular languages?
I think that is fine. You just need to explicitly state that this is a regular language, this is a regular language, and this is a regular language.
Right.
And then you could say, since each of those are closed, which is identical to,
almost what
we
you
know
said.
how to construct interface.
Yeah.
Right, because that's exactly what we were doing in the theorems.
I was just wondering.
Yep, so that's another way that you can think about it, completely logically equivalent. Any other questions? Cool. We'll see you next week. Remember to try and reply to the Facebook event, whether you're coming or not coming, so I know who's coming, who's not coming. I usually create the event within like an hour after the class, so you should have plenty of time to see it and do it.